Hello, everyone. Welcome to this week's algebraic graph theory. And this week we have Erika and Pirnes to talk about minimum relations for an algebra inspired by the algebraic graph theory.
Yes, so thank you for inviting me to this seminar. Yes, so let's get going. And the main idea of the talk, well, we find minimal relations for an algebra, and this algebra is called balanced algebra. And yeah, I was invited to give one talk, but I will actually give two talks. So one is the 5-minute version of the talk first. Then I'll talk about the goal, the origin, and then about the results. But let's start with the 5-minute version. Okay. So, well, we're finding minimal relations for the balanced algebra. That's the goal. So I have to tell you what the balanced algebra is. So it has two generators called R and L. Then there's something called a balanced word. So these two words are balanced. Why they're balanced is because they have the same number of R's and L's. The last example, that's not a balanced word because it has too many L's compared to R's. So balanced words play an important role. So basically, what are the relations? They are balanced words commute. So if I take any two balanced words, I should be able to swap those. So here's an example, LR commutes with RL. And now let's look at one example in the balanced algebra. So if I look at this element, this word on the right, I first have an L, then I have this pair of two balanced words, and then an R. And now if I'm looking inside the balanced algebra, I'm allowed to switch these two things in the middle. So these two words would be the same in the balanced algebra. But now if I organize the parentheses a little bit differently, I actually notice that I can write it in another way, which is actually uh, effectively by switching something inside the word, I have actually switched these two other balanced words. So it seems that this relation LR commuting with RL is somehow a better relation, so to say, because it implies this other relation. And we'll get back to more examples later. So basically our question is, what is the minimal set of pairs of balanced words that I want to require to commute so that all balanced words would commute? So for example, in the previous example, if I allow R and RL to commute, well then this LLRR and LR will also commute. So that's not the second one is not required anymore. And what is the origin? This problem comes up in algebraic graph theory, or something similar comes up in algebraic graph theory. So if we have a certain type of graph, it has this algebra called Terwilliger algebra, and it's generated by matrices R, L, and some matrices EI star, a bunch of matrices. So R is called raising operator, L is lowering operator. And then very unmathematically said nice things happen when balanced words in R and L commute. So what that nice thing is, the graph is thin. We don't have to care about that right now. I'll go more into detail in the full version of this talk. Okay, and then what my main result is, I give an explicit minimal set of relations, or actually it's a family of these minimal sets of relations. And in quotes, the set looks like a bipartite graph. I'll explain what that means. So we have two different kinds of words, special words. So here's an example of something I call an upper prime. Prime because it has very strong analogy with prime numbers. So what prime means, it's a word that I have so first of all, I visualize these words because R means raise, L means lower. So every time there's a line going up, that's R. Line going down, that's L. So A prime word is something that I start from some level, I do something, and then in the end I come back to the same level, but not before. Because if I come back to the same level, something before, I can write this word as a product of smaller words. So prime means I cannot write the word as a product of smaller balanced words. And upper just means we first do R. Lower means we first do L. So these special types of words are in play in this diagram. So basically, what does this diagram mean? All of the squares are equivalence classes. So on the upper level, there are equivalence classes of upper primes. Lower level equivalence classes of lower primes. And what does this minimal set of relations look like? It looks like we choose a representative from each class, then we require the representative to commute with all the representatives on the other level. So of course here I only drew 3 of these boxes, but there will be actually infinitely many, but I couldn't fit them all on this slide, so that's why I did 3. Okay, and I think this was my 5-minute version. So now we can actually start the talk, and I'll talk more about what is the goal. Okay, so what are we doing? We first start with a free C algebra with these 2 generators. And if we're a little bit more precise, we're actually going to define this this balanced algebra as a quotient. So as I said, a word is balanced if it has the same number of both generators. And now I consider the ideal J, which is generated by all fg minus gf, where f and g are any 2 balanced words. And basically, yes, so the balanced algebra is a quotient by this ideal. And then just to have some notation, this is nothing complicated, but so there's an equivalence of words. Word 1 equivalent to word 2 if their difference is in this ideal. So if they're the same in the balanced algebra. So the very same equivalence that always with quotient. It just makes some things simpler to state. So in the 5-minute version, I talked about these equivalence classes. This is exactly the equivalence I'm talking about. Okay, so what is our goal? We find a minimal generating set for this ideal J. And to state, be very clear of what we're doing is we want to find a minimal generating set that is a subset of the original set. So maybe there could be theoretically there could be some other generating set which like some crazy looking generators which is like smaller in some sense, but the problem that I'm working on is finding a minimal generating set that is a subset of this original set. So all the generators are of this type fg minus gf. And that's what we mean by finding minimal relations. Okay, and then let's do some examples. So as we saw already, this LR minus RL this is element in this ideal J. And then the previous example we had, these 2 words are equal because I can write their difference as something times a generator of J times something. So that will be in the ideal. And then something related. So if I'm kind of in the previous example, I did like one swap. I swapped this LR and RL. But if I do more than one swaps, this corresponds to a telescopic sum. So I just have an example here, not a concrete example because it would be confusing. So let's say I transform W1 word into first W2 and then W3 by swapping something inside the word. So now I can write W1 minus W3 as the telescopic sum. So I'm kind of doing one swap at a time. And all of these, so all of these generators of J kind of look like swapping words. So if we look at the general element, always looks like a word times a generator times a word, and of course it can be a C-linear combination of those. And that kind of element, word times generator times word, it corresponds to swapping something inside the word. Okay, and now I'll talk about the origin a little bit more in detail. So for a certain bipartite graph, the Terwilliger algebra T is generated by matrices R, L, and some matrices EI stars. And I'll just give an example of a cube. So this is a bipartite graph. I colored the vertices black and white. And here I have labeled the vertices in a special way. So let's start with down at the bottom, I have vertex A. And then the vertices that are of distance 1 from A, I have B1, B2, B3. Then distance 2 from A, C1, C2, C3. And then distance 3 is this vertex D. So basically, I have kind of the labeling tells me about the subconstituents of the graph. So 0th subconstituent, everything at distance 0, well, that's only A. At distance 1, distance 2, distance 3, so on. So basically what we're doing, we take a vector space, 8-dimensional vector space with basis indexed by the vertices. And then the raising operator and lowering operator, in this case, together give the adjacency matrix. So if I go back here, what does raising operator do, let's say, to B2? It sends it to the formal sum of vertices that are in the upper subconstituents. So here it would send it to C1 and C2. And now if we look at the raising matrix, this B, which one I was looking at? I was looking at B2. So it would be A, B1, B2, that one. And here we have ones in these places which correspond to C1 and C3. And a lowering operator does the other way. So B2, it would send it to A, and then adjacency matrix just sends the vertex to every vertex it is adjacent to. So that's the thing. So here, let's look at this third column. So this would be the B2. We had this C1 and C3. If we look at the third column here, sending to A, the first vertex here, and then if you look at the third column in A, we have all of them. And I think that's enough. So basically, the EI stars, then they are the projections onto these subconstituents. So if I talk about subconstituent, it can mean the set of vertices in the graph or the subspace corresponding to that basis. So if this one, it corresponds to, let's project onto the subspace that is generated by or spanned by the vector A. This one would be the BIs, CIs, and D. And I think this example is enough to kind of have an idea what is happening. So then I'll talk about T modules. So what is the standard module V? It's the vector space that came up in the example. So in the example, it was the 8-dimensional vector space. So in general, it has as many basis vectors as the graph has vertices. And then V is the direct sum of subconstituents. We just looked at that in the previous example. And what is the T module? It's a subspace of V closed under the action of T. So all matrices in this algebra T, if I act on the subspace, I'll still stay in the subspace. And a T module is called thin if all intersection with subconstituents have dimension 0 or 1. So basically what this implies is that a thin T module, we can find a basis for it so that every basis vector belongs to a different subconstituent. So it's some nice condition. So then there's this result that says all irreducible T modules are thin if and only if balanced words in R and L commute. So this is where the problem comes from, what I'm working on. And irreducible here just means like, oh, we cannot find a proper submodule. And just a note here, so the abstract R and L behave differently than their matrix versions. So for example, if we look at the matrix R, in our previous example, in the 8-dimensional case, if I just take a high enough power of R, I'll get 0. But with the abstract R, that just never happens. I can have like as long as I want R, and that never becomes 0. So basically, my problem is inspired by this situation, but not quite the same situation. So I'm only looking at the abstract R and L on only those relations that balanced words commute. Okay, and I think this is enough for the origin part. Okay, so now let's go to the results. So first of all, I've already been talking about this kind of this swapping perspective, and of course it might feel not so rigorous, and I agree, it doesn't feel that rigorous, but so first of all, let's look at, there's a result I've proved that actually if I take the ideal approach, I can use my own swapping approach, and they're actually the same. So what does it say if I take any two words, if their difference, x minus y, is in the ideal generated by some set of these generators. So I guess I should have said these FIs and GRs are balanced here. So then what we get, then x can be transformed into y by consecutively swapping adjacent FIs and GIs. So it's like similar than we saw in the example. The easy direction is like, oh, if you can go from one word to other by swapping something, then definitely yes, that difference x minus y is in the ideal because you can write it as a telescopic sum. But the backward direction, the one direction here, is not that easy, because in the first place, like, not, let's say x minus y is in the ideal, it doesn't have to be an integer linear combination. If it was, then it was pretty easy, but like it can be some weird linear combination. But the idea is that, okay, well, if x minus y is in the ideal, then we can actually find an expression of x minus y in that ideal as that looks like a telescopic sum. So I have a very, very non-mathematical proof here, or a proof. So this is basically just the idea that was kind of guided, the intuitive idea that guided finding the actual proof. So I call it the domino proof, and I'll explain what this means. So basically, so x minus y, now it's in this ideal. And what does the ideal generators look like? They look like something minus something. So that's where I get my domino blocks. Like, it has the positive and negative end. And now if, well, x minus y is a linear combination of terms that look like this. And of course, C linear combination, there are some coefficients. Let's forget those for a second. But in somewhere x appears. X has to appear somewhere, the word x. So now the block that x is in, it has the negative side. And let's say this negative part here is not y. So of course, if it's already there, then we're done. But like, let's say this is not the word y, but then it's some other word, and because x minus y is this linear combination, this word doesn't appear in the actual result. So there's something canceling it. There's another block with a positive sign. We cancel it, and then we kind of go forward. Then that block has a negative part, and that get canceled, and so on and so on. And some point we reach y. And this is not quite how it works, because like there might be the case that we start with x and then we actually get back to x. But the idea is that actually there has to be such a path. Such a path exists, and this is by no means a proof. This is not a valid argument for this, but this is kind of the guiding idea, that this kind of situation has to happen in order for x minus y to be in this kind of ideal. Okay, and let's see. So basically a couple of corollaries. So let's say I start with a product fg. If I cannot transform it to gf without allowing the obvious swap fg, then fg minus gf is in all minimal generating sets of j. Well, let's see, let's look at the previous result. Let's say I take every other pair than f and g. I allow those to commute. I take the ideal generated by all these pairs fi gi g minus gi fi, like in this proof. But now if fg minus gf is in that ideal, well then I can actually transform fg into gf by swapping these fi's and gi's. But now if I cannot do that, if I only swap I can make is the f and g, that's a contradiction. So therefore one of the generators of j has to be this fg minus gf. I cannot remove that generator. And when, of course, if I say in all minimal generating sets, in all minimal generating sets that look like that are a subset of the original set. Okay, and then corollary, second corollary, so x equivalent to y if and only if x can be transformed into y by consecutive swaps. So what did this equivalence mean? It meant x minus y is in the ideal. Well, now we just use the result. X minus y in the ideal in the j means x can be transformed into y by consecutive swaps. And yeah, so I don't know if I said it, but basically, why did I want to make this change of perspective? It is because it makes some proofs really nice. And I don't mean the domino proof. That was a fake proof. Okay, so some terminology. So as I mentioned earlier, prime words. What is a prime word? It is a balanced word that cannot be written as a product of shorter balanced words other than the empty word and itself. So analogy with the prime numbers. So some examples, some prime words on the left, on the right, not a prime word because we can write it as a product of RL times RL. Okay, and then some more terminology. So upper primes start with R, lower primes start with L. And then just something to note, if any two prime words commute with each other, then any two balanced words also do. And this is because, let's say I have my first word, it's a product of primes. Yeah, any balanced words can be written as a product of primes. Second word, product of primes. Well, if I want these to commute, I can kind of, commute the little primes one by one, and then I'm done. So that's the idea. And just to know, there are infinitely many prime words. So for example, R n times, and then L n times. And so then something to note about upper primes before I go to the next intermediate result, is about if I have an upper prime, I can write it as R, a product of upper primes L. And I think I have a picture here. Yeah, so an example, because the word is a prime, it means that we never return to the level we started from until the very end. So now I can draw a line here on the level 1, and that's like the lowest the word can come down to, like in the middle. So I first have R, then in this case I have product of two upper primes and then a L in the end. And this has a role in the next result. So basically the result says if all upper primes commute with LR, then any two upper primes commute with each other. And the actual proof is by induction, but here I have a picture proof that kind of explains the process. So I start with, this is an example. So I start with two upper primes. On this picture 1, I have two upper primes. And basically, what am I doing here? My assumption is upper primes commute with LR. So now I can use it. I notice that if I draw this line on the level 1, I have the first upper prime, there's the product of upper primes, the two ones here. Then I have L and R, and then I have here the product of upper primes, it's just one upper prime, just to keep things simple. So basically I can commute this LR with this upper prime. So I'm moving this one at the end. And then next step which we're doing, so actually it would be induction, but I'm reducing the process to smaller, shorter upper primes. So these were longer upper primes here. Now I'm this word that looks like letter M, I'm switching it with the smaller peak and then with the bigger peak, one by one. So moving it to the end. And now, what can I do? This LR piece here, I can switch it with these upper primes, the smaller peak and the bigger peak. And now when I do that, I have effectively switched the two original word. I have this big M here move to the front, and then this other word moved to second. So basically, what did we use? We used the assumption upper primes commute with LR, and then smaller, shorter upper primes commute with each other. So the actual proof is by induction on the total length of the pair, showing that any two upper primes commute with each other. And so kind of from this follows another intermediate result. If any upper prime commutes with any lower prime, then any two balanced words commute with each other. So what did we get from the previous result? We get that any two upper primes commute because, well, what was the assumption? It was if any upper prime commute with LR, then any two upper primes commute. Well, if any two upper prime commutes with any lower prime, then obviously any upper prime commutes with LR. So we have the assumption of the previous result. So we get any two upper primes commute. Similar result, we just switch the roles of L and R. We get that any two lower primes commute. And then the thing I mentioned before. So if any two prime words commute, then any two balanced words commute. So just kind of shifting one by one, and then we get that. So what can we conclude? We could reduce the generating set of J to elements of the type UD minus DU, where U is an upper prime, D is a lower prime. And this is still not the minimal generating set. It has too much stuff in it, but it's a reduction for sure. It's a smaller, well, still infinite, but smaller set. Okay. So I think this is the last intermediate result before my main result. So if U is an upper prime and D is a lower prime, then any possible swaps inside UD, other than the obvious swap U and D, happen inside U or inside D. And this is a very short picture proof. So basically we have an upper prime first going up, lower prime first going down. And now if I look like, what does a swap mean? I need to have a product of balanced words in order to be able to swap. So I need to have a level that I start from this level. I first go up and then down, or I go up, and then I can switch those. But now let's look at here. So if I look at the level 0, the only swap I can do is the U and D, the illegal swap. If I look at levels that are above, well, then all the swaps on those levels happen inside the upper prime. If I look at levels that are below, all swaps happen in the lower prime. And of course, I've written a more mathematical proof than look at the picture. But I think the picture just makes it easier to understand what is happening. Okay, so basically, what is our conclusion? In order to be able to swap U and D, I need to swap some U prime and D prime, where U prime is equivalent to U and D prime is equivalent to D. So basically what's happening here is that if I want to switch these two, I either have to switch these, or I could first, let's change this first word. I have first the smaller peak, then the bigger peak. Well, maybe if I swap those to those first, that's not the same word anymore. Then I can swap these two bigger words and then kind of switch back. Then I have achieved this relation UD equals DU from something else. But basically, in order to do that, I need to be able to swap one representative for the class of U and one representative of the class of D. That's what I need. Without that, I just cannot do it. And that's what this result tells me. Okay, and I think, yes, we're ready to state the main result. So basically what are we doing? We're choosing a representative for each equivalence class of upper and lower primes. And just for convenience, that's it. I call these UI and DI. So infinitely many equivalence classes. And I choose the representatives. Okay, so basically, what are we doing? As I drew the picture, which is actually here, so from each equivalence class, I choose a representative. I need that to commute with all of the representative in the other categories. So representative of upper prime have to commute with all the representatives of lower primes. And again, infinite. This diagram should be infinite. Okay, so the set UIDJ minus GJUI, any pair of indices, that's a minimal set of generators. So from the previous result, we got that we need to get so the previous result said we need to take at least one representative, assume those to commute. But then it's a little bit more work to say that this is actually still a generating set. But that's not too bad. Okay, so I think I am done. Yes, and here are some references. And yes, thank you.
Okay, thank you, Erika, for this nice talk. So, is there any questions for Erika?
Sorry, is it possible to use coding theory literature because Word is so close to coding theory, for example, or reversely, some analogous between balance for prime work in coding theory, like Hamming code or something like that? or is it a direction to get a special ideal or algebra to get some result for some classes, or characterizing minimal generating set for a special class? Is it a direction to go, or it makes sense about this idea?
Yeah, so I think that's interesting question. So I don't know that much about coding theory, so I don't think I'm a correct person to answer that, but maybe someone in the audience would have an idea.
Thanks.
Any other questions for Erika?
Erika, have you done any research on this problem when it comes to groups themselves? Like if you take the free group and you take the normal subgroup that you get from balanced words commute, has there been any work done on that question?
As far as I know, no, but like, yeah, maybe someone has done something and I'm not aware of it, so.
Okay, and a follow-up to that, if you look at the finite images that you would get by like your Q example, where you add the relation r to the n equals is trivial, and L to the n is trivial. Do you know what dimension that this balanced algebra has?
No.
I'm just thinking that combinatorially that should be possible to use your result to say, you know, how many UIs and DIs would be available.
Probably.
Yeah. Okay. Okay. Thank you.